Before we start, um, first of all, some things about scheduling. We haven't yet taken a conference photo, so we're proposing to do that in the first coffee break immediately after this talk. So what we thought we'd do is go down on the lawn, see if we can catch some of those tortoises and have a conference photo. Then after that, the order of Faye and Raphael's talk have been reversed, sort of local time reversal, as it were. So we've got Raphael immediately after the first coffee break, and then Faye is the last talk.
Yes.
After the second.
Yes.
Yes. After the second coffee break, then we'll have lunch, and then we've decided to compress the round table discussion a bit. So we'll just have a 1 hour session at lunch, finish from 3 to 4. Then at 6:30 there'll be buses for dinner. So we've got dinner booked at a place down in the city. Dinner is booked for 7. There'll be a bus pick up here at 6:30. Okay, so now I'm going to hand over to Daniela.
Doesn't stand for that. Thank you for inviting me here. Okay, so in a fair number of people's opinion, general relativity is not only a relativistic theory of gravitation, but also a freeing of physics from background structure, i.e. ideas of background independence. And then quantum gravity would appear to imply very much one of these things, but there is also another notion, quantum background independence, that one would expect to have something to do with GR as well. And then at least some quantum gravity programs would involve both of those, and then the QG would stand for a quantum gestalt rather than for quantum gravity, to note that both of those are being placed on similar footings. And then there are quite a lot of models which cover only relativistic theories of gravitation, although there are quite a lot of theories that have both of these features in them. And then there are some models that are models only of quantum background independence, or at most have only Newtonian gravitation in them, and among those are the relational particle models, and those are the toy models that this talk will use quite a lot. So then, the basic idea is that if one considers background independence to be a theoretically valuable notion, background independence implies the problem of time. So it doesn't make sense to do the opposite, to avoid the problem of time by incorporating background independence, as occurs in certain parts of the literature. I'll get on to what background independence is eventually. It will need to be explained as the talk goes along. For the moment, I'll just give names.
Just a little bit higher.
Oh, yeah. You're losing the bottom, okay. There we are. There are some examples of theories that incorporate one of the features or both. Covariant gravitational theories, I think I'm going to point on the slides, like perturbative theories of gravitons or perturbative strings, are only really about some sort of Einstein field equations or approximation to Einstein field equations or things like that. Whereas other things, like the dynamical formulation of GR, geometric dynamics, and attempts to quantize that, and loop quantum gravity, and supergravity and M theory have enough width and breadth that they can be considered as theories that incorporate background independence as well. So those manage to have both of the sets of features. So these sorts of theories here, they have a full-blown problem of time, whereas things like gravitons on fixed backgrounds or perturbative strings have less or no problems of time in them. So the problem of time is something that has to do with wanting to have background independence. We'll start with what's well known about the problem of time, and that comes from the reviews of Isham and Kukash from the 1990s. Now, many papers say, and this is often because papers have to be short, that the problem of time has something to do with the equations being frozen when one has quantum mechanical versions of general relativity, the Wheeler-DeWitt equation and so on. But one of the main points of these very good reviews, is that there's not one facet to the problem of time, this frozen one, but there's actually 8 of them, and they're listed in different colours along the boxes there. And I won't comment on them for the moment, because I'm going to be interested in changing the names of quite a few of them, because I don't think those names are quite right. They don't fully cover what the problem is or identify it in most clear terms. So we're going to be changing what these are anyway. And that changing process is when I'll explain what each of these is. Furthermore, as well as the thing having 8 facets, they're interlinked, which is rather unfortunate. They're interlinked in a very unfortunate way indeed. What Kukash said is that if you solve 2 or 3 of these and then try to face a 4th one, then typically what happens when you solve the 4th one is that you find that you haven't solved any of the first 3. So this is not one of those things where you make progress by having solved some and then adding on to that by solving a subsequent one. It's a more complicated problem than that. It has a tendency to fight back. Nor is it a closed problem, because sometimes, if one tries certain strategies for dealing with these, one finds that one can trade one of these time problems for something which is not a time problem. For instance, if one goes for a timeless approach, then many of these things that have to do with properties of time functions will go away. But all the timeless approaches appear to require non-standard interpretations of quantum mechanics and things like that instead. Also, in Raphael's talk, he'll be doing it a path integral way, whereas this talk is about canonical ways principally, although there's also histories ways here to some extent, but there are different sort of histories. But if one does a path integral approach, then one loses some of these, and one finds that one gets actually other problems of time instead, and one also gets, in part, a measure problem. So it's not always about solving these. Sometimes you can trade one of these for something else, but whatever you trade it for, it also is hard. So there's no known way to solve this thing, at least not in general. I'll present a model for which quite a lot of it can be solved, but it's a very simple case. And here's a summary of what the situation was as regards strategies for solving these things, again, from the 1990s. Being faced with an equation that has no time in it, you might claim that it's got a time hidden in it, and you tend to want to find that at the classical level, so it's a time before quantization. Or one might add on some sort of matter that provides a time or something like that. Or one might accept that the equation is timeless, but that then one expects time to emerge under certain circumstances, the most obvious of which are almost homogeneous universes and in semi-classical regimes. Or one might take the timelessness at face value, and in the Isham and Kukash reviews, as well as things like naive Schrödinger interpretation and conditional probabilities interpretation and Ravelli's approach, they also classified histories theory as a type of timelessness. Now, I disagree with that and classify it somewhat differently. I think that, okay, you can swap the idea of needing time for needing history, but it's still requiring some sort of structure, which other of the timeless approaches are more minimalist and don't require. So instead of having this division into 3, I believe there actually ought to be a division into 8. The first 3 along the top here are the same as theirs, but then as well as tempus ante-quantum, there can be historia ante-quantum, and as well as tempus post-quantum, there can be tempus post-historia. And this is also allowing for the possibility that there's no quantization for the other 3. It might not be appropriate to quantize GR, and Carlip wrote a review about approaches like that this year, so that's what you should consult for those. They won't feature any further in this talk. But it is possible that one might just use time and no quantization, or just use notions of histories and no quantization, or one might use neither time nor histories nor quantization in the most minimalist case of them all. So there's logically 8 possibilities here, but there'll only be 5 of them, the first 5 on this side in this talk. And as I said, if you want to know about the other 3, then Carlip wrote a review about that sort of thing. And that's okay. So where does the problem of time come from? It comes from an incompatibility. There are 2 sorts of time in theoretical physics. There's the time that features in Newtonian mechanics and its quantization, which is much the same as the one that features in special relativity, relativistic quantum mechanics, and quantum field theory. That's one sort of time on the one hand, and there's the one in GR on the other. Now, there are some differences between this column and that one. They have different notions of simultaneity, as is well known. However, what happens in passing from this column to that one is that one is trading one set of absolute structures for another. So here one has the well-known Newtonian space and time, but here one has Minkowski space-time and all its associated killing vectors and things like that, which are entirely atypical from a GR point of view and constitute a fixed background. In GR one gets around that because the metric now is one of the dynamical variables rather than the Minkowski metric being something which is prescribed and unchangeable by anything that happens in a Minkowski model. So that's the main difference between this set and that set. There isn't so much difference between those. These are all still types of absolutist structures. Okay, so then next thing to observe is that, as one can guess from saying that the problem of time follows from background independence, and background independence is already something one can conceive of classically, then one's going to expect that there's going to be at least antecedents of the problem of time, most of the problem of time facets, that are already present in classical theories. So in full GR, they're obviously all present, because that's where they were found. So yes. Where is that? Oh, that's classical GR, okay. But in full quantum GR, they're all present. That's this row here. In full GR at the classical level, they're all present except for the so-called multiple choice problem. And the multiple choice problem is a purely quantum mechanical problem. We'll get on to what it is later, but for the moment the thing to note is that it's one that's not present at the classical level. So at the classical level there's at best 7/8 of the problem of time present. Moreover, one observes that even in mechanics, formulated in a suitable way, which is the relational particle models, one finds that 5 of the problem of time facets are already present there. And of course, mechanics is a very easily understood theory, and it's very easy to do calculations with it. So if 5 of them are already present there, then one can derive quite a good conceptual understanding simply from mechanics. On the other hand, that's largely not been done before now. But what has been studied quite a lot as a simpler model than the very hard case of the full GR is mini-superspace. In mini-superspace, there aren't any of the problems that follow from there being linear constraints. On the other hand, there are various other things present in some way which are absent from mechanics. So those two models to some extent complement each other, and they have a similar number of features that are similar to GR's, but they're different in each case. So in a very loose way, it's a bit like if GR were a manifold, and the particle models in the mini-superspace were some sort of charts on it which can be used to study different parts of it, and then there's some overlap between those, and in fact there's a better chart called midi-superspace, which covers the features that are present in both of those at once. But the trouble is that that is already pretty hard to do calculations with. So many calculations become inaccessible for that or haven't been attempted yet. So although midi-superspace would be better placed to do the calculations than either of these two things, mini and relational mechanics models that are in this talk, it's too inaccessible, and it would take me a number of years to repeat the calculations in this talk for that. And it's entirely possible that some of them would come across obstructions. And of course, there's two sorts of obstructions. There's the obstructions that mean I just don't know how to do it, but there's also obstructions that involve no-go theorems and things like that. So there may be obstructions that are not down to my incompetence. The next slide is one which appeared already in George's talk. However, George didn't comment too much on it. This is the structure of general relativity as a dynamical theory, where it's now the dynamical object are the 3 geometries. This is usually done from the point of view of having GR expressed as an action principle, and the first line here is general relativity in a space-time form, the so-called Einstein-Hilbert action. Rich is the Ricci 4-scalar here with respect to the 4-metric G. And one takes this G, and like Arnowit, Deser, and Misner, splits it up into an induced metric, a shift vector, and a lapse function. And these are to be interpreted by considering what happens in passing from one spatial slice to another. The lapse is the amount of time elapsed in moving between the two surfaces, and the shift has to do with being some sort of point identification map for where this point on this surface ends up on the next surface in its coordinate system. The next thing that occurs in these sorts of approaches is that these spatial slices are embedded in the space-time, and they're bent in a particular way. And that means that they have an extrinsic curvature. And extrinsic curvature has to do with being relative to the space that something is embedded in. So as one knows, a cylinder is flat, as is manifest from how you can make one out of a piece of paper. Although it seems that slides are harder to make one out of. So it's just as flat as it was before, but now it has extrinsic curvature. And the formula for extrinsic curvature involves, well, a shift term, but also the rate of change of the spatial metric. And it's got the lapse as some sort of proportionality factor. So then one can write the action in terms of these things, so that the action itself has been split and is now an Arnold-Desser-Misner action. So then one splits the volume element into a lapse and the volume element of the 3 space, and this thing here splits up, according to the embedding theorems, in fact, doubly contracted Gauss law or whatever, things like that, into a part which is the Ritchie 3 scalar of the 3 metric H, and also another part which can be interpreted as the GR kinetic term, and which is quadratic products of this. And this is essentially a more complicated version of Gauss's Theorema Egregium, outstanding theorem that relates extrinsic curvature to intrinsic curvature in the case where the overall space was flat. This is a generalization where one is doing the same for a curved space, and it's higher than just a 2D geometry and a 3D geometry, so it takes this slightly more complicated form. Then from a canonical perspective, the extrinsic curvature are further interesting because they're essentially the same as the gravitational momenta. If one varies this action with respect to the h dot, then there's one h dot in each k, so one essentially ends up with the k's being what fits the definition of the conjugate momentum to the h's. It's not quite right. There's a densitization factor, a lapse factor, and there's a correction because there's 2 terms here, so the other one contributes as well. So there's some kind of trace subtraction or something like that. At least at a conceptual level, the gravitational momenta is more or less the same as the extrinsic curvature. Then, with a system of equations like this, if one varies with respect to the shift vector, one gets the momentum constraint. And that is telling you in a passive sense that the coordinate transformations on the surface are irrelevant, although one can also phrase it in terms of active diffeomorphisms. So it has to do with 3 diffeomorphisms on the slice itself. Variation with respect to the lapse, on the other hand, gives you a quadratic expression, whereas the previous one was linear. And that will be significant in how this talk and various other practitioners choose to treat these constraints in a different fashion. To write it in a fully dynamical form, one would summarize the information in here using some kind of matrix prefactor, which then plays the same sort of role as masses and things like that do in mechanics. So it's a kinetic metric. And for general relativity, the kinetic metric is the inverse, in fact, of the DeWitt supermetric, which itself features in rewriting the Hamiltonian constraint. So this combination here then involves the inverse of the kinetic metric, which is the DeWitt supermetric. So that's what GR looks like as a dynamical theory, at least in the more old-fashioned picture, which suffices for this talk. Okay, so then the way that the frozen formalism problem is commonly presented involves noting that the Wheeler-DeWitt equation is like this equation here, which is a stationary, i.e. frozen Schrödinger equation, rather than this equation here, which is a time-dependent Schrödinger equation, which you might be expecting. Now, if this was occurring for the GR case itself, you would need a functional derivative rather than a partial one, and it would also be satisfactory from the point of view of the thing being unfrozen if it was some wave equation other than the time-dependent Schrödinger equation, maybe more like a Klein-Gordon equation or something like that. But the point is that it doesn't have any time in it in any form. And it's also often acknowledged that this follows from the Hamiltonian constraint already at the classical level being quadratic rather than linear. And now I'm going to change the way that people think about this. I'm going to argue that this frozenness is already present classically and that you put it in order to model background independence in the first place. I derive it from assuming as a principle, as a demand of a type of background independence, Leibniz's statement that there is no time for the universe as a whole. Now, philosophical statements can be slippery if they can't be implemented with sharp mathematics, but it's easy enough to implement this one with sharp mathematics. One can use a manifestly parameterization irrelevant action, which is quite clearly the same by cancellation of labels, as in this pink working here, to a manifestly reparameterization invariant action, which involves a label, but where the label doesn't mean anything because you can trade it for any other label. In the case of mechanics, first of all, this action is rather well known. It's the Jacobi action. In the case of GR, there are equivalent actions of this sort, the first of which was written down by Baylane, Sharp and Wheeler in 1962, and it takes this kind of form here. So it looks very much the same as before, except, of course, there's a notion of space that one has to integrate over, and one has a more complicated kinetic arc element associated with the inverse DeWitt supermetric now. Okay, that's one condition for implementing the principle. The other one is that the principle cannot be cheaply implemented by involving extraneous time-like variables like the Newtonian time or the GR lapse. But these actions indeed succeed in not having that present. If one tried writing down difference-type actions of the more common sort, like Euler-Lagranges or ADMs, one would find that those do involve T Newton or alpha. And the two things are equivalent because you can eliminate T Newton or alpha from those. It effectively features as a multiplier or as a cyclic velocity of something else. And then one can get a very easy, simplified Euler-Lagrange equation from that, and one could solve it for these variables themselves and then pass to either of those two actions there. That would either be a multiplier elimination, or in the case where it's a cyclic coordinate, it would be a passage to the Routhian. Yes?
Just a trivial question. I just want to make sure I'm roughly on the right track. In the mechanics case, so this is an action such that by minimizing it or by taking an extremum, you get a trajectory in the usual way?
Yes.
You get a trajectory, but by trajectory you mean something like position as a function of time?
No.
Okay.
The trajectory is a path in configuration space.
What parameterizes it?
Nothing, because although you could parameterize it with a label time d lambda, if you parameterized it with any other d mu, then the two would be entirely equivalent. So it doesn't need to be present at all, and one can think about it simply as a geodesic principle. Right. So if you like, you can already see something that's going to be present here. There's a notion of change here, yes, because there's a path in configuration space, so there's a notion of dq as well as of q, where q are the configurations, but there isn't any notion of time. Okay, and how does this work? You noted before that in the ADM formalism you needed to vary the lapse in order to get the Hamiltonian constraint, which is the crucial thing, but now here you don't have a lapse. So have you lost that equation? No, because not all equations in the principles of dynamics arise from doing variations. There are also equations called primary constraints that arise purely from the form of the Lagrangian. And Dirac argued, entirely convincingly and entirely simply, that reparameterization invariant actions have to have at least one primary constraint. Because being reparameterization invariant, they're linear in the velocities. That means they're of zeroth order in the momenta. And that means that they're a function of ratios of momenta, and then you don't have enough momenta for all the momenta to be independent. Therefore, there must be a relation between them, and that's exactly what a primary constraint is. So, one indeed expects that one is going to get the Hamiltonian constraint, or its energy constraint equivalent from the mechanics case, from that primary argument. And indeed, the square root forms of this action give you, by some sort of generalization of Pythagoras, the forms of the equations that we had before. And in the mechanics case, it looks like this, and that's just a mass and some delta functions in the matrix, and it's written in an unreduced form. I prefer taking the center of mass out, and instead of using particle positions Q, using Jacobi vectors R. The R's are like particle positions in terms of how they feature in the equations. The equations look exactly the same as before, but with one of those less. What they are physically is not particle separations, but particle cluster separations. So some of them are allowed to run from centers of masses of particles to other particles rather than just between particles. So with these present, Sorry. Okay, I'll stand a bit further across. Okay. Yeah, I can just about reach the point. Okay. So that's one of the problems of time, one of its facets reformulated. We're going to reformulate another one now. It was originally called the so-called thin sandwich. And this was due to Wheeler in the early 1960s. In fact, the same paper as Bailyn, Sharp, and Wheeler. And there's two sorts of sandwiches, thick and thin. So in the thick one, you have two of these spatial hypersurfaces, and you're interested in constructing the space-time in between them, which is very obviously sandwich-shaped. The trouble is that it was very soon shown that this sort of procedure is not very well defined mathematically. So instead, one wanted the thin limit of this, where one prescribes the 3 metric and its derivative, and one tries to construct a small sliver of space-time as one moves away from that. And it's not like, this is not to be confused with something like a GR-Cauchy problem, because here one is specifically solving the momentum constraint at the Lagrangian level for the shift vector, and only after that does one build up the extrinsic curvature tensor and get the space-time region. So it's a very specific procedure, and that's actually important for how it features in the time-finding process. Okay, but the one reason that calling this problem the thin sandwich is unsatisfactory is that thin sandwiches have to do with hypersurfaces and with diffeomorphisms, and therefore with theories like GR. But we're considering the problem of time as something occurring in a very wide range of theories that have background independence that are not necessarily GR-like. So another example of this is Barber's comparison of two triangles. So he keeps the green one fixed and he shuffles the blue one around until it reaches maximum congruence with the green one, and then chooses the value of the rotation for that. There the rotation is playing exactly the same role as the shift vector is playing in the thin sandwich. So in fact, Barber's best matching is a theory-independent generalization of the thin sandwich, and is therefore a better name for the thin sandwich problem facet than the thin sandwich was itself. Moreover, one can understand that this sort of thing has something to do with frame fixing or something like that, and that doing this procedure is implementing a type of background independence. But there's nothing in implementing background independence that demands that it has to be done at the Lagrangian level. So this particular sort of background independence itself is called configurational relationalism, and it's only talked about as best matching then when it's attacked at the Lagrangian level. But if it's called configurational relationalism, it could be attacked at the Hamiltonian level instead, or even at the quantum level. And then one has a much more well-known word for what is specifically best matching in this Lagrangian case. The word now is reduction. And one usually does reduction in phase space or something like that. Or consider some sort of reduction at the quantum level in a so-called Dirac quantization scheme, where the constraints survive through to the quantum level, and then one deals with the linear constraints first as a restriction on one's preliminary Hilbert space. The way to think about configurational relationalism then is, as well as one's configuration space Q, one has a group G of irrelevant transformations, and one models this in a way that's accessible mathematically by adding auxiliary variables G. But then you might say, well, you already had redundancies in the Q, you now add the G's, you've just doubled the redundancies. That's true, but because the constraints that follow from the G's are linear, they happen to be the sort of constraints that use up 2 degrees of freedom each. They are so-called first-class constraints, and this is, of course, recognizable as not quite what is usually presented as gauge theory, but rather definitely equivalent to it. So what happens then is that one passes from Q to some sort of G bundle over Q, but once one takes into account the constraints that arise from varying with respect to the G variables themselves, one ends up on the quotient space Q over G, and in doing so one has succeeded in rendering that G irrelevant. And when this G has something to do with the transformations of space, be they rotations in mechanics or 3 diffeomorphisms in the case of GR, then it's quite clear that this is implementing some sort of background independence. But the configurational relationalism indeed doesn't care what the G is. So it also includes the G in the well-known case where the G is an internal group, as occurs in the usual sorts of gauge theory, like electromagnetism and Yang-Mills and so on. So configurational relationalism is both at the same time spatial relationalism and internal relationalism. And the basic way to implement it is, if you have an object that doesn't respect this, then you act on it with the G's, and then you do some sort of operation that uses all the G's at once. So you act and then you use all of them. And in doing that, the 2 uses of the G's cancel each other out, at least formally. and in practice as well when you can actually do the construct. And one example of this is best matching, where one corrects the velocities with respect to the g's, and then one extremizes with respect to the g's in order to remove them. But it's not the only example. In the theory of the geometry and statistics of shape, there is something which fits exactly the conceptual description that I've given now, which is called the Procrustes procedure. It involves exactly the same two moves, it's just that it doesn't involve an action, so the thing that one is extremizing is a different object, but it's the same sort of G-act, G-all construct. And another example that is very well known in basic mathematics and basic physics is group averaging, as occurs, for instance, in representation theory to prove a number of simple facts about some of the easier groups. So that is also a G-act, G-all method. The G-act, G-all method generalizes all of those, and it's how one implements configurational relationalism at whatever level of structure one cares for, be it the Lagrangian one, the Hamiltonian one, or at some stage in the quantum procedure. So that is the most general thing. And then in this case, the G are rotations, and in this case, the G's are three diffeos. Now, it's then true that a lot of features of the diffeomorphism specifically are very important in order to solve the more complicated aspects of the problem of time that we'll get on to later. So the rotations are not good enough as a model for this, because there's many important diffie-specific features in general relativity itself that need to be addressed. But to understand this picture that I've given here, the rotations are enough to elucidate that this is the right way of thinking.
So G is like some kind of symmetry group?
It's just some sort of symmetry group.
Why do you say quotienting with respect to that is background independence? Surely I would have thought cashing out background independence on having a nice big so there's no kind of structure that's perfect.
It's saying there is no absolute origin because you quotient out the translations. There is no absolute rotation. There's no absolute. Mm-hmm. Well, you can't choose. The way I'd put it is that you can't just choose any G for your Q, because there are some G's that are not natural for that Q and that don't have any group action and so on. So if you try using just any G, you might find that your system of equations tells you back this is not consistent. So there are a certain number of restrictions on what you might be able to do in this procedure. But certainly in the case where it's something like rotations, translations, scales, if you consider scalings to be irrelevant, you're getting rid of absolute space structures. Likewise in GR, you'd be getting rid of the coordinatization.
So you mean particular bits of background?
Mm-hmm. It's also saying that in electromagnetism, the gauge things are physically irrelevant. So it's getting rid of things that are unphysical in all cases for sure. The next one was called the problem of observables, but observables imply being observed, and that's not very useful for early universe cosmology and so on. There's a notion that's already appeared in some of the other talks called beables, and beables just imply being. So this is Bell's notion. So on this basis, I prefer calling it the problem of beables to calling it the problem of observables. The technical definition, the most important part of it for observables in constraint theories, is that they're to commute with constraints. It's often taken to be the case that they have to commute with all the constraints, in which case they're Dirac observables. But one might say that those linear constraints that give things which are like gauge theory are the ones that matter, and the Hamiltonian constraint is allowed to produce some sort of evolutions, and therefore you don't expect the objects that you're using to describe physics to be invariant under that. So there is a case that can be argued to not consider the quadratic constraint among the constraints in the definitions, and if one does that, one is considering Kukash observables, and one is then ensuring that one's variables are gauge invariant in the usual sense, but one is not trying to extend that to have a gauge invariance as defined such that invariance under the evolution itself is among the gauge invariances. And finally, one could consider neither of these conditions, and then one would be trying to deal with something like Ravelli's partial observables. So that's a further weakening still. So Dirac observables are the ones that are hardest to find of them all, which is why Kukash, in setting up Kukash observables, described Dirac observables as unicorns. It's very good to say that you can use unicorns in your quest to deal with the problems of physics, but then you have the problem in practice of actually being able to find one and it deciding that it's going to choose to let you ride it. So finding Dirac, essentially, In general relativity, even classically, very little is known about finding observables. And for quantum gravity, then the situation is worse. Okay, next. This one they call the functional evolution problem. But I don't like that because it refers to functional derivatives that are present in the equations. It has to do with brackets closing, essentially. In finite theories, you have partial derivatives instead. So if your theorizing involves all theories, it has to involve some sort of derivative that is sometimes partial and sometimes functional. And I call that the partial derivative. And it's a logical consequence of how Kukash and Isham place a lot of emphasis on distinguishing between functions and mixed function functionals that they describe like that. But when one is treating theories that have an object occur in this form, being used as models for objects that occur in that form, the most natural form to write then is a portmanteau of the two. And then when one considers the equivalent derivatives, well, unfortunately there's quite a lot of types of derivatives, so you get more than one. And I write them, in this case, I write the whole of the partial symbol and the whole of the delta symbol as well on top of it, so that one can tell from looking at it what it's the portmanteau of. And then, those are the other two portmanteau derivatives that occur here. Those are partly ordinary derivatives. So this one's half partial, half ordinary, and this one's half ordinary, half functional. So a better name than functional evolution problem is partial evolution problem. However, that still implies that it's at the quantum level. If one considers the classical antecedent as well, then a much simpler name for this problem is the constraint closure problem. It's just that then, at the classical level, one has the good fortune that this is often true, so that it's a problem which is then resolved. The three diffeomorphisms have no difficulty at all closing up. They close as this Lie algebra here. If you did the four diffeomorphisms, you'd have exactly the same, but with something bigger than the shift vector. However, if you split the space-time with respect to a foliation, then the algebra becomes more complicated. The Poisson bracket between the momentum constraint and the Hamiltonian constraint just says that the latter is a three-diff vector. That's not a problem. But the one between the two Hamiltonian constraints, it features a combination like this. If it was a Lie algebra, this thing here would be a constant, but instead it's a function. So it has structure functions instead of structure constants. So it closes in a complicated way. And that'll cause a lot of problems later, but at least it closes. So the constraint closure problem is resolved at the classical level. It's just that then at the quantum level, generally the commutator doesn't even have the same algebra as the Poisson bracket. And also, how one operator orders one's constraints will clearly affect what commutators they do and do not obey, and there isn't a clear prescription for how to do that. And then finally, it's well known that at the quantum level, there are things called anomalies that arise. There are algebras that were perfectly well behaved at the classical level, and then their quantum counterparts have obstructions that say, no, you could declare that was a classical symmetry, but it's not a quantum symmetry. Quantum mechanics forbids it. So because of that, although the Dirac algebra tidies up things nicely at the classical level, it's not at all clear what happens at the quantum level. Two more problems. Foliation dependence problem. Moving between this slice here and that slice there, it should not depend on how the cloud of observers that is looking at this moves. So if they move via the red foliation and they move via the blue foliation, the physical results on the final surface should be the same. That is a nice and intuitive and background independent notion. And it was demonstrated by Teitelbaum that this is true at the classical level thanks to the properties of the Dirac algebra. However, at the quantum level, we haven't got the faintest idea if this nice property continues to be the case or not, and if so, how you demonstrate it. There's also the case that one has a space-time reconstruction problem. This is usually stated at the quantum level, but one can already ask at the classical level, what happens if one assumes the three spaces and does not assume that they sit inside a space-time? Can one derive that there's a space-time surrounding them? And the answer to that is yes. The Barber-Foster-Omerhu work, Relativity Without Relativity, is precisely a derivation of that sort. At the quantum level, things get worse. The trouble is, at the classical level, you have a choice to a larger extent. You can think about space-time or you can think about evolving spaces. But then, in quantum theory, it's the dynamical objects that fluctuate according to the usual picture. So the three spaces undergo these red fluctuations here. Trouble is, once they undergo those fluctuations, they're not all embeddable in the same space-time, so the notion of space-time has somehow dissolved away, an observation of Wheeler's from the 1960s. And then, yes, If one assumes less structure still, like discrete models or almost discrete models and things like that, one still needs to recover a space-time in a suitable limit, i.e. when it's semi-classical or classical or something like that, it needs to give back a space-time. So then it's part of that. And if one doesn't like the notion of space-time or thinks that something else needs to be in its place, then it might be called a replacement instead of a reconstruction. Okay, now, the next part of this talk is going to give a local resolution of the problem of time. So it's essentially going to cheat and not look at two of the facets. However, it's a problem which is conceptually definable without the two. So it's somehow the most excusable two that can be left out. I'm going to solve all 6 problems semi-classically for a relational triangle. And then I will try to have time to show a picture of how one might try to do the same for GR, which involves a number of things that are broken that I identify as the next problems to work on. Okay, now the multiple choice problem essentially has to do with choosing 2 different times at the classical level, maybe entirely equivalent to each other, but there's no reason why they ought to give equivalent quantum theories. Something as innocuous as passing from the variables q and p to q cubed and p cubed, that doesn't do anything at all classically. It's trivially a canonical transformation between the two. However, if one promotes each of these things to operators in separate theories, one then finds that the 2 theories that arise are inequivalent by the so-called Groenewald-van Hove phenomenon. And then, of course, q and p could be times, or they could be frame variables, or they could be observables, in each of which cases this thing is relevant for various problems of time. So that's how the multiple choice problem works. And finally, the word local hides that there's no global considerations. Those could be global in space or global in time. So it could be just a piece of a Cauchy surface that one knows about or can deal with rather than the whole thing.
The fact that the different quantization of classical theory exists independently of any problem of time, why do you call it problem of time?
Sorry, which one?
The fact that there are different quantization of classical theory,
Mm-hmm.
it by itself has nothing to do with problem of time.
It does, because if you have a time which is chosen among the Q's and P's, most obviously in an internal time approach, then it would be different choices of time that would give different quantum theories.
I did not make myself clear. This problem exists also when there's no issue of time around.
Yeah, the Q and the P could be absolutely general Q's and P's. It's just that the Q could be a time function.
So it's just a restating of the fact that there will be different quantum theories at the same classical units.
Yes. But one of the ways that this can happen is through different choices of time. Classically, in GR, you can say time is a coordinate, I choose this coordinate, I choose that coordinate. Then you come along and do a quantum theory and find you get a different quantum theory for each of those things.
So it's not the problem itself, it's specific instances.
Yeah, it's like not all anomalies are problems of time, because some anomalies have to do with internal symmetries. But there are some anomalies that depend on choices of times and frames. So it's a subset of multiple choice that's specifically a time multiple choice. But there's also a frame multiple choice and an observables multiple choice. So even if you have no time, you still have observables, so you still have a multiple choice problem there.
Are you saying that you can quantize different gauges, and if the symmetry is a normal symmetry level, the different gauges will not be equivalent?
That's part of it, but not all of it. Because what I was saying about the anomalies was logically separate from this, but in certain cases the two will conflate.
You have 10 minutes.
Well, let's try to resolve it now. Let's see how far we can get with that. Okay, we answer Leibniz's there is no time for the universe as a whole. With Mach's, time is to be abstracted from change. So then a priori the emergent time is a function of the change in the configurations. The next issue is what change? You might consider any, you might consider all, like Barber does, but what I consider is a sufficient totality of the locally relevant changes. I give all the changes the opportunity to contribute, but I don't include the ones which then turn out to contribute negligibly for the physics that one is trying to do. And both the all approach and the sufficient totality of relevant change approaches are inspired by 20th century astronomy. They found the moon wasn't where it was meant to be in, I don't know, the 1890s and 1900s, sometime like that. So they started working on new lunar theories to explain that. But then de Sitter suggested that this is because the hypothesis that the sidereal time reads off the Newtonian time was false. due to irregularities in the rotation of the Earth, essentially, due to magma currents, tidal effect, and things like that. And taking that into account, using the Earth-Moon-Sun system as a larger clock, one found that that was consistent, and that then further things that were not included within it, like the motion of the planets and so on, was consistent with that too. So the way it goes essentially is that sidereal time is only a good time to about 1 part in 10 to the 5. If one then wants to work up to 1 part in 10 to the 11, the Earth-Moon-Sun system is fine. After that, relativistic effects come in, and you have to start asking where this time that you're talking about is defined and so on. And by that stage, one started using atomic clocks instead to get that kind of accuracy. But there was this basic idea that somehow the time here is being abstracted from change. If you include more change, the time can be more accurate, but only when the more changes you're including are relevant ones. So here the moon was relevant, but say Andromeda wasn't. So you can't just include anything and expect it to get much better. So that's what I mean by sufficient totality of locally relevant change. And times of this nature are called ephemeris times. So what I have here is a generalized local ephemeris time. Is being abstracted from a sufficient totality of locally relevant change. And by calling everything local here, you can do special and general relativized versions of this locally. They're just as good. You can still have astronomical times these days, defined now, but they have relativistic effects built in. They're not Newtonian, but post-Newtonian expansion or whatever. All of that's included in that sort of resolution. So then, what particular one do you have? You start off with something like the Jacobi action for mechanics. You get equations of motion. You find that if you use this combination here for your time, which is here written without the labels, then it simplifies the equations of motion, which suggests that it ought to be adopted. But adopting it like that means that it was never put in. So although this object is mathematically the same as the Newtonian time in the mechanics case, it was gotten at by starting with a purely relational system that didn't have one, and then finding that this one gave you the simplest equations of motion, and then choosing it for that reason. So it's a relational recovery of Newtonian time. And in the GR case, this thing recovers you the proper time, or in the cosmological case, the cosmic time. So all of those come out now as emergent relational times. And that's how one resolves the problem of time. It's frozen formalism facet at the classical level. However, if your theory has non-trivial configurational relationalism, you have the problem that that extremum condition is required for this object. Because that object itself then included G corrections, so if one doesn't do some G removing operation, one doesn't know, because one's trying to compute a frame-dependent quantity then. So you get a frame-independent one if you perform the extremum, but performing the extremum has to be the extremum of the action, and it has to be solved for the G variables. That means that in the GR case, you're stuck with a thin sandwich problem, and you can't trade it for a nicer phase space problem, or anything like that. So you're stuck with a very difficult PDE that there's been very little progress with for 50 years. Problem 1. However, for the relational triangle, this is easy to solve. In fact, it's easy to solve for all relational mechanics models. But for the triangle model itself, you find that the reduced configuration space is the sphere. In the scale case, it's the cone over the sphere, which is R3. So then you have some very simple thing like this, which is written in terms of the reduced variables, which has replaced this extremum condition in a theory that had non-trivial configurational relationalism. So here it's solved. Then, if you can do that reduction, you automatically have Kukash-Beables. In the scale case, they are the shapes and some scale variable, which is here the total moment of inertia, and their conjugate momenta. Any functional of that lot will serve as a Kukash variable for the system. So you've got the Kukash-Beables sorted out for you. Then there's a construction of Halliwells. In fact, there's two, and they're different, and one doesn't promote to the other. But you can do it both classically and semi-classically. You can build objects that commute with a quadratic constraint. So, if you started off with your theory formulated in Kukash-Beables, because you got this far, you can then apply this procedure and get it to commute with the quadratic constraint as well. So then it commutes both with the 5 minutes, you say. Okay. It commutes both with the linear one and with the quadratic one. So it's a Dirac-Beable, and in this case you've succeeded in constructing toy unicorns. To end this thing off classically, the RPM constraints happen to close. There's no such thing as foliations or spacetimes in this simple model. It doesn't claim to have those GR features. So we're done to level 1. Yeah, unfortunately, that's not very far. Disaster. This emergent time does not unfreeze the quantum quadratic equation. However, if one applies the semi-classical approach, one can derive an equally Markian time which succeeds in doing exactly the same. This is not exactly the same as the usual semi-classical approach, although it uses a lot of its mathematics, stuff from Banks and Halliwell and Hawking. However, It's been reformulated such that additionally it's a Markian scheme. And then you find that the emergent WKB time, as it's called, of this approach, if you consider lots of corrections being ignored, it comes out the same as the one you had before. So it's consistent in that way. However, what's going on, remember, all change has to be given an opportunity to contribute. This is a quantum theory. It has quantum change. Of course it's going to give a different time in general, right? And that's exactly what happens. It's the same to zeroth order, but then it has a correction in terms of quantum changes and other quantum effects. Expectation values, results of operator ordering, etc., they all come in and give you a slight change. But it's as Markian as before, and the difference between them is perfectly Markian as well. So the Markian scheme survives the transition, at least to the semi-classical regime. Then, well, we already resolved configurational relationalism at the classical level. If you reduce a theory, it stays reduced when you quantize it. So you're through on that. And I said that Halliwell had a scheme that does that construction of Dirac Beebles at the semi-classical level as well, so we can take advantage of that. And now, because it's a reduced scheme, it only has one constraint, and one constraint always closes with itself. No constraint closure problem. It's a relational model of these particle type, so it has no foliations and no spacetimes. So, for a local theory, are we done? Unfortunately not, but from now onwards, I even say here, not just because I'm out of time, I'm going to flash through these slides for the expert. Okay. The semi-classical approach relies on the WKB assumption. This is not a good assumption a priori. So instead, one needs to find some reason why that occurs, and the best reason that we have involves decoherence providing it. And Halliwell's scheme involving these things that were being used as Dirac Beebles, that uses history theory inputs. So one has to start again from level 1 and build up a timeless theory and a histories theory as well, and then do those at the semi-classical level too. And that involves using all the work that's summarized here, and that provides the upstairs and the downstairs of the handle. One also needs the double combinations between all these theories, the links, and then the triple combinations. And the triple combinations are described here as the handle classically and the blade quantum mechanically. And the most significant part of this is the blade, and this is currently based on Halliwell's 03 paper about the problem of time. The best matching itself is the pommel. That's relevant for the end slide. Okay, now what does the blade involve? Well, maybe we'll put that up at the end so it can be read more. The blade involves this combination here of conceptual supports between those three strands. That means that although they don't stand well alone, like cards don't stand up on their edges, you can build card houses by supporting cards against each other. And this is how the blade supports itself. The handle is much less interesting because a lot of the parts of the blade have to do with decoherence and computing semi-classical timeless probabilities, which are not notions that occur semi-classically. So at the classical level, there's much less motivation for the lower part of the handle, except it's the quantum antecedent of this much more significant combination in the blade. So that's how the scheme works together at the level 3. Halliwell's construct itself, for anyone who's interested, is this, and it involves a so-called class operator that has to do with the probability of trajectories or histories entering a region, so it's a histories concept. And there's two open problems with this scheme. That blade has not been demonstrated in cases that involve non-trivial diffeomorphisms. And this construct for Dirac observables has not been either. So those are open problems 2 and 3. Then, let's do GR. Now, instead of there being no foliations and no space-time reconstruction, and the constraint closure problem being trivial, one can't get away so cheaply. One needs a second weapon, Dirac's trident. Classically, I've already told you, the Dirac algebra closes. Teitelbaum showed it implies foliation independence. Hodgman, Kukash, Teitelbaum, and then Barbara Foster and Merku, and myself, and Flavio Mercati, space-time reconstruction, all at the classical level. The problem is, do you know how to do the equivalent of this semi-classically? Answer is no. Open problem 4. However, we do know how to do this trident in the case where it's homogeneous, classically and quantum mechanically. Homogeneity implies one constraint, so it closes with itself. Homogeneity implies much simpler foliations and much simpler space-time structure. So for many superspace, this is sorted. So what's the idea then? To model this specifically in the case that Halliwell and Hawking's inhomogeneous perturbations about mini superspace. So then to the 0th order this happens. To the 2nd order you throw away the 2nd order and then you just have linear terms, semi-classical terms, but they're non-trivial diffeos nevertheless. They're the easiest non-trivial diffeos than you can find. So the idea is that you'd construct the semi-classical trident for that first because it's easier and then try to extend it. Okay, so then we have a list here on the end slide what the problems are. Problem one, thin sandwich. Problem two, the blade is not known to work with non-trivial diffeos. Problem three, the Dirac observables are not known to work with non-trivial diffeos, so you don't know how to capture real unicorns rather than toy ones. Problem four, you don't know how to build a trident that's long enough. And then there was the A and the local condition that I said was removing two problems of time. And then finally, there are some unsatisfactoriousnesses with using classical regions to implement quantum propositions, because classical regions combine Booleanly and quantum propositions don't. And that's what I'm working on with Cecilia. So those are the 7 frontiers of this approach that need to be cracked in order to be able to do this thing for GR. And then I end with the references and just the final names of what I consider the 8 facets to be. So you can note those down rather than the original ones, because they're the processed final product. That's all.
Time for a few questions. That was a stunning summary of these, beautiful summary. Now, I'm always really interested in what of this is testable, what has been tested, what is not testable. I would really like to see your talk and other similar talks have overlaid on it a set of contours of what is well-established tested physics, what is moderately conjectured, what is way out conjectured, which parts of this are certain. For instance, the Newtonian and special relativity, that's incredibly well tested in its domain of applicability. The Wheeler-DeWitt equation has not been tested in any context whatever, and probably never will be tested in any context whatever. I think these contours of certainty should be overlaid on the
That's one of the reasons that I concentrate on semi-classical approach. From a quantum gravity perspective, that is a very modest aim. On the other hand, this semi-classical approach gives you semi-classical quantum cosmology, and that is then hoped to be a quantum cosmological origin for the structures that inflation increases in size, and then give you the galaxies and the microwave background pattern. Now, admittedly, that working there has a number of conjectural steps, and this sort of thing has not been demonstrated yet. But you can kind of understand how, if inflation continues to persist as a leading theory for cosmology, then this sort of approach might be testable within 10, 20, 30 years.
The trouble is inflation is such a flexible theory. Inflation is a multiple branching animal.
Yeah, but hopefully some of these features are not very theory dependent. That's one has to hope on. But because of that, it's the most testable end by also being the most modest end, and that's a semi-classical quantum cosmology end. There are a few other things that I said. That, I said something like, foliation dependence. It seems to be something which would be crazy classically. We would like to keep on forbidding that at the quantum level, but we don't actually know whether it's true or not. For that, you might imagine that there could be experimental tests or a thing like that, although these are not in any sense realistic. But sometimes you might be able to theoretically overrule it. You might be able to show that there are obstructions and get very general no-go theorems theoretically, which would then require you to cease believing that that's a good property to carry over. So occasionally the theorizing might be able to cut things out by itself. And in other cases it would provide at least, if you like, thought experiments or experiments that aren't restricted by realistic experimenting conditions. So things like that could be attached to a number of the facets and what is being done. I agree with that, and it's something that's worth working on.
I think one can separate two different problems. One is what is the kind of physics, what is the boundary between the physics tested, testable, and not. And this boundary, I think with me, is very clear, and there's not much doubt about it. The tested part is a very large part of classical general relativity, is a standard model theory. And in fact, it seems to me we are in a remarkably funny position in the history of science in which this boundary is particularly sharp. Rarely has been so sharp, actually. And everything else is just not tested. Not tested.
If it ever has the label not testable.
Not tested, not easy testable so far. The only thing that is easy testable so far, seems to me, is supersymmetry, and the indications are strong against it. So that's where we are. However, that's what I wanted to say. It seems to me
demonstrate that the universe is, after all, absolute by experiment, and do so at the classical level.
If you could do that, I want to encourage you to do
Well, 1 pi in 10 to the 5 is well away from current cosmological accuracies about these things, where the Hubble is only known for 1 pi in 10 to the 2. But, 3 orders of magnitude is much nicer than, 30 orders of magnitude, and 15 orders of magnitude, those being typical numbers that prohibit other sorts of quantum gravity
The reason
tests.
quantum gravity is so difficult to think about testing is, it has little to do, in my opinion, it has little to do with how far away is the Planck scale, because I think the standard we got about that is completely wrong, in my opinion. There was a very good theory, a wonderful theory, which was SU5, 7 nanometers ago, which everybody was convinced about it. It was very convincing, which has been, it's a sort of prototypical comparative case in science. Sometimes they happen. It was falsified by a very specific experiment, which is proton decay. It's a clean experiment that was a prediction of that theory is false, so that theory is being discarded from. And if you look what this experiment is, it tests energy at a scale which is immensely higher than the CERN scale of proton decay, and it's just 2/2 times the Planck scale. So it's not that by itself impossible to do experiments at that scale. It's just very hard. It can be done. Would you agree with this?
Yeah. Well, some of the most interesting experiments with these runs, when you look at the sharpness of propagation of light over cosmic distances.
Of course, that's another case in which Lorentz, hypothesis of Lorentz invariance violation had been falsified to over transquantum scale. So we do have access to that. We do have some access to that scales. Unfortunately, at the moment they don't give us much.
Just kind of going back to the question I asked in the middle of the talk about what you mean by background independence. So I sort of understood this to mean something like you don't put the, say, the geometry in by hand, or one way of trying to cash that out is in terms of writing a dynamical geometry. But that didn't sound like the answer you gave to me. So imagine I had a theory that just was in some Newtonian space-time. It sounds like you would say it was background independence if I just had some way of quotienting out all the space-time symmetries.
In that
But that
particular...
doesn't sound background independent in the first sense of not putting the geometry in by hand or making the geometry dynamical.
There are quite a lot of senses in which something can be background independent or not. Some have to do with things like absolute space and absolute time. Some have to do specifically with whether you're introducing metrics or not. But if you're introducing diff classes of metrics, that's not the same as introducing metrics. But one might want to introduce less, and ultimately one might want to say, well, those hypersurfaces you're including there, they all have the same fixed topology. Isn't that a background dependent structure as well? And the answer is yes, but we don't know how to get rid of it yet. So one can always, whilst one has levels of mathematical structure that one is assuming, one can always try to assume less and call that background independence or an increase in background independence. So the answer is there's lots of sorts of background independence. Sorry, and in this approach, because it's a dynamical approach, space background independence and time background independence are treated separately. So that's why there's temporal relationalism and configurational relationalism. But it's not claimed that those are the entirety of background independence. There's also background independence context in the foliation independence, for instance, and there are further types too. So
How does this get I would suggest you continue over the coffee break. So let's thank the speaker again.
Okay, now we're going to go outside for a photo photography.
So this is a fan of the projector.
Can we put this projector off?
It's on the far end, it's a P300 glass.
Oh.
Yeah.
But if this is, you said P300, it's a part number.
Yeah, yeah, but
It's a part number P300.
Yes. Is it possible to turn this off?
As long as they on still.
It's still going to fan.
Yeah. No, but I can hear it.
can you hear that buzz?
Yeah, you can hear it anyway, yeah.
How many of you on the transformer here?
Well, there's only one per transformer here. So it's a mission to get into these panels. They're all wonky, and the transformer sits on top, and it's very heavy.
Is that on the standard transformer in or out transformer?
No, standard transformer. We just did 1-for-1s.
If you replace one with halogen, glass system while the others are on, is it still on? You try that. It's not really back normal.
We haven't tried that.
Because they never got a charge yet. Because the wind's.
It might be an easier solution. Just have one halogen per.
Yeah, because it's usually
It's the load.
load related. They've got the electronic transformers, they're keeping that one at 1 watt. It's still only, it shouldn't be doing that. I know, but you've got
it's wire
the
one.
standard, it's the wire one.
Yeah.
That's,
We can try it
just try that and see what happens.
instead of redoing the whole thing.
But this humming sound can be the sound of the transformer itself.
It is.
It is the transformer.
It's not the lights.
Yeah, it is the transformer.
Yes, because the halogen is supposed to make it.
The television was not coming.
It's humming because there's not enough load on